Okay, in this lecture we're going to cover our section 2.6 material on quadric surfaces. So let's define what a quadric surface is, and then we'll consider the different types of quadric surfaces. So starting with the definition, a quadric surface is the graph of a second-degree equation in three variables, say x, y, and z. Now, the most general type of such equation would be something of the following form. Let's say that we have ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus some constant j is equal to 0, where a through j are constants. So this is the most general second-degree equation in three variables, which is quite complicated looking because it involves so many terms. However, by translation and rotation of surfaces in three dimensions, we can reduce this equation into one of two standard forms. Either ax squared plus by squared plus cz squared plus some constant j is 0, or ax squared plus by squared plus iz is equal to 0. Now, in these two standard forms, these variables, x, y, and z are interchangeable. So in particular for this second form of the equation, well, it doesn't always have to be z to the first power. We could have a second degree polynomial in terms of say y and z, and then have a single term involving x to the first power. But nonetheless, it would have a form, the equation would have a form very similar to this. Now, when we're talking about trying to sketch the graph of a quadric surface, we're going to use something called traces. So in order to sketch the graph of a quadric surface, we're going to consider what the curves of intersection of this surface would be with planes which are parallel to the coordinate planes. So those would be planes parallel to the xy plane, the xz plane, or the yz plane. And these curves are called traces of the surface, or sometimes just cross-sections of the surface. So now that we've defined what a quadric surface is, a graph of a second-degree equation in three variables, and we've defined traces, which would be the intersections of our surface with these planes parallel to the coordinate planes, let's introduce the different types of quadric surfaces and see how we can make use of traces to visualize what our surface looks like. So the first one that we'll start with is one of the easier surfaces. The surface defined by an equation of the form x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. So we can see that this is somewhat similar to the equation of a sphere in space. However, our coefficients for x squared, y squared, and z squared are different constants. So it's sort of like a warped sphere, which gives us something called an ellipsoid. And to visualize an ellipsoid, let's think about its traces in each of the coordinate planes. So I claim that all of these traces are going to be ellipses. So here I've given a graph of an ellipsoid in space. Let's sort of justify why our graph would look like this, or think about how to visualize this ellipsoid if the graph wasn't given. So I mentioned that the traces in each of the coordinate planes are ellipses. So let's consider the different coordinate planes. So for the xy plane, which is the plane z equals 0, let's see what our equation for this surface becomes. So if we substitute z equals 0 into this equation defining our surface, we would be left with x squared over a squared plus y squared over b squared is equal to 1. So we see that this equation in two variables represents an ellipse with x-intercepts of plus minus a and 0. So to find the x-intercepts of this ellipse in the xy plane, we would set y equal to 0 in the equation for this ellipse. It follows that x squared is equal to a squared, so x could be plus or minus a. And then we would have y-intercepts given by 0 plus or minus b. So in the xy plane, let me maybe color code these. So in the xy plane, which is the plane z equals 0, we saw that our intersection of the surface with this plane would give us an ellipse whose x-intercepts are at plus and minus a, 0, and whose y-intercepts were at plus or minus b and 0. So we see here that we have this ellipse traced out in the xy plane. So that would be called, or this curve, this ellipse in the xy plane is called the trace of our surface with the plane z equals 0. Now let's think about some of the other traces and other coordinate planes. So let's think about maybe the y z plane. Or maybe I'll start with the xz plane. So the xz plane is the plane defined by y equals 0. So if we take the equation of our ellipsoid and we set y equal to 0, we would have x squared over a squared plus z squared over c squared is equal to 1, which again defines an ellipse whose x-intercepts are plus minus a and 0, and whose y-intercepts are, or excuse me, not y-intercepts, but here we're in the xz plane, so our z-intercepts would be 0 plus or minus c. So let's look at this trace in the plane y equals 0. So in the xz plane, we would have an ellipse whose x-intercepts are at plus minus a, and whose z-intercepts are at plus and minus c. So here we could trace out our ellipse in that plane. We would get a curve that looks something like this. So looking at our trace in the last coordinate plane, that is the yz plane, which would have the equation x equals 0. Let's see what we have. So substituting x equals 0 in the equation of our ellipsoid, we have y squared over b squared plus z squared over c squared is equal to 1, which again defines an ellipse with its y-intercepts at plus minus b 0, and its z-intercepts at 0 plus minus c. So in the yz plane, we would have an ellipse whose y-intercepts are negative b and positive b, and whose z-intercepts are positive c and negative c. So if we trace out that ellipse, we would have the following curve shown here. So if we were to also consider planes which would be parallel to these coordinate planes, we could see that we would get ellipses in those parallel planes. So if I consider planes which are parallel to that xz plane moving outward along the positive or negative y-axis, we see that we also get ellipses. And similarly, we would have ellipses in these other cross sections parallel to these other planes. So visualizing our traces for these surfaces as ellipses, we can visualize what our surface looks like. And this sort of surface, which was sketched here, is called an ellipsoid. So let's consider some other quadric surfaces. And the idea is going to be the same here. We're going to be considering what our traces look like in different coordinate planes or in planes parallel to those coordinate planes. So our next type of quadric surface will be the one defined by an equation of the form x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. So it's similar to the equation for an ellipsoid, but one of my terms in that summation on the left-hand side has a negative coefficient, say for instance z. So this quadric surface is called a hyperboloid of one sheet. So it's sketched here below. And to visualize or justify why our surface would look like this, let's consider its trace in different planes. So I claim that its trace in any horizontal plane, z equals k, is an ellipse. So let's start by looking at traces in horizontal planes. So those would be planes that are parallel to the xy plane. So substituting a constant value, k, in place of z, we would have our equation as x squared over a squared plus y squared over b squared is minus k squared over c squared is equal to 1, or moving all of my constants to one side of the equation, we would have the following. So here, since k is a constant, we can move this k squared over c squared term to the right-hand side of our equation, and we would have the sum of x squared over a squared plus y squared over b squared is equal to some constant. So this equation defines an ellipse. And we see that the larger the magnitude of this constant k, I would have an ellipse of larger and larger area. My intercepts would, my x and y intercepts would be increasing. So as I move outward from the xy plane, my ellipses get larger. So in general, we have ellipses. And if I look at the particular trace in the xy plane itself, which would be the plane z equals 0, so if I take k equals to 0, we would have an ellipse with its intercepts as x being plus minus a 0, and its y-intercepts being 0 plus or minus b. So if we visualize this, well, we would have our x-intercepts in the xy plane being plus minus a 0, and our y-intercepts being plus minus b 0. So we would have this ellipse shown here. And I mentioned as we would increase the value of k in the positive or negative direction, so as we increase the magnitude of k, we start getting ellipses of larger area. So our x and y intercepts would increase, but in any of these planes that I take parallel to the xy plane, I get an ellipse. Now let's consider what our traces look like in other planes. So I say its traces in either the xz or the yz planes, or planes parallel to these, would be hyperbolas. So let's think about maybe the xz plane. So here in the xz plane, which would be the plane with equation y equal to 0, our equation for this quadric surface would become x squared over a squared minus z squared over c squared is equal to 1. And this would represent a hyperbola in a plane. So here we would have a hyperbola whose x-intercepts would be plus minus a and 0, and it would not have z-intercepts here. So if we're considering our curve, let me maybe color code this again. So in our horizontal planes, we had ellipses, which were sketched here. If we consider in the xz plane, we have a hyperbola whose x-intercepts were at plus minus a, and it has no z-intercepts. So here our hyperbola in that xz plane would look something like this. Okay. Now in our other coordinate plane, that is in the yz plane, which is the plane defined by x equals 0, the equation for this hyperboloid would be y squared over b squared minus z squared over c squared is 1. So this again defines a hyperbola in the plane, in the yz plane, with y-intercepts of plus or minus b 0, and does not have any z-intercepts. So let's see if we can sketch this trace. So in our yz plane, we have a hyperbola whose y-intercepts would be positive or negative b and 0. So in that yz plane, we would have a hyperbola that looks something like this. So by visualizing those traces, we get an idea of what our solid looks like, or our surface looks like. We can see it sketched out here in full detail. So this is called a hyperboloid of one sheet. So what's the deal with the one sheet thing? Well, we use that term to distinguish a hyperboloid of one sheet from the next type of surface that we'll discuss, which would be a hyperboloid of two sheets. So let's consider this. The quadric surface, which has the equation negative x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1, is called a hyperboloid of two sheets. So again, this equation is similar to the equation that we had for an ellipsoid, but where two of our quadratic terms, say for instance the x and the y terms, have a negative coefficient and the other is positive. So let's see what this surface looks like and how it's distinct from a hyperboloid of one sheet. So here I mentioned that its traces in the xz and the yz planes are hyperbolas. So let's start with those traces, and then we'll consider traces in horizontal planes. So starting with the xz plane, which would be the plane y equals 0. Our equation would be of the form negative x squared over a squared plus z squared over c squared is equal to 1, which defines in that plane a hyperbola with x, which does not have x-intercepts, but here with z-intercepts of plus or minus 0 plus minus c. So if I'm listing x first, my x values would be 0, and my z values would be this positive and negative c. So let's see if we can sketch that. So in the xz plane, we're having a hyperbola whose z-intercepts were at positive or negative c. So here, sketching out that hyperbola in the xz plane, we have something that looks like this. Now in the yz plane, which would be the plane where x is equal to 0, our equation reduces to negative y squared over b squared plus z squared over c squared is equal to 1. So again, that defines a hyperbola in that plane whose z-intercepts are again plus minus c, and where it does not have y-intercepts. So for our next trace in the yz plane, we have a hyperbola whose z-intercepts are also plus or minus c. Now if we're looking at a hyperbola in the yz plane, we would have a hyperbola that looks something like this. So let's consider the last type of trace, a trace in horizontal planes. So here, it's a little bit tricky. We have some sort of restriction as to when our surface will actually have a trace in a horizontal plane. So let's consider what that restriction is. So here, I mentioned if the magnitude of k is greater than z, then the horizontal plane z equals k would intersect this surface in an ellipse. However, if the magnitude of k is less than c, then the plane z equals k does not intersect this surface, and hence it consists of two parts. So let's see if we can justify that. So if we're considering in the trace of this surface in horizontal planes, so those are planes parallel to the xy plane, which would be defined by z equals some constant value of k. Our equation would become negative x squared over a squared minus y squared over b squared is a plus k squared over c squared is equal to 1. So if we move everything with a variable to one side of our equation and everything with constants to the other side of the equation, we would have the following. So I could rewrite this equation as k squared over c squared minus 1 is equal to the sum of x squared over a squared plus y squared over b squared. So I would recognize this as the equation of an ellipse. However, this is only an ellipse if this equation has real defined solutions in that plane. Now looking at what we have, so let me coordinate this as we're going through with the color. So I would have an ellipse provided that I've got real solutions to this equation. Now let's look at our right-hand side. On the right-hand side of the equation, I'm adding x squared over a squared plus y squared over b squared. So since everything is being squared, I know that this right-hand side must be non-negative. So the only way that I could have real valued solutions here is if this constant on my left-hand side is greater than 0, or greater than or equal to 0. So we have an ellipse for our trace as long as k squared over c squared minus 1 is non-negative. So that is if k squared over c squared is greater than or equal to 1, which means that k squared has to be greater than or equal to c squared. We're taking the square root of both sides. The magnitude of k has to be greater than or equal to c, where we're assuming here that c is a positive constant. So here, in the event that k would equal 0, if we're talking about the xy plane itself, I would not have a trace. And we can see here that in the xy plane, my surface has no intersection. There is no trace in this xy plane. It's only if we take k large enough, so that is if I move far enough upward or far enough downward from the xy plane, that I would start to see ellipses. So my traces in these different horizontal planes would be ellipses, where the larger that I take the value of k, that is, the farther I move outward from the xy plane, the area of my ellipse gets larger and larger. So since there is some plane in which there is no trace, our surface consists of these two distinct parts. So here we would have what's called a hyperboloid of two sheets, as opposed to that one sheet hyperboloid that we had considered previously. So let's look at some other ones. So the next type of quadric surface we'll discuss, which would be defined by the equation z squared over c squared, is equal to x squared over a squared plus y squared over b squared, is called a cone. So here we could also define this equation. An equivalent representation that we'll see throughout this course might be if we were to move the c squared across so if we see something of the form z squared is equal to the sum of constant multiples of x squared and y squared, then we have a cone. Now, the traces of this surface in horizontal planes, say something of the form z equals k, would be ellipses, and its traces in vertical planes, say x equals k or y equals k, would be hyperbolas or lines in the event that k is equal to 0. So let's take a look at these different traces. So here, let's start with traces in horizontal planes. So if we're considering planes of the form z equals to k, then the equation for our surface is given by k squared over c squared is equal to x squared over a squared plus y squared over b squared. So here we would have ellipses. So we recognize this as the equation of an ellipse for any value of k. And the larger that we make this value of k, that is the further that we move above or below the xy plane, our ellipses would have a larger area. So in these horizontal planes, z equals k, we have ellipses where the further that we move upward from the xy plane or downward from the xy plane, as we increase the magnitude of k, we're going to have these different ellipses. Now let's consider our traces in other planes. So let's consider vertical planes that are parallel to the YZ plane. So that is if we're taking x as a fixed value k, then the equation reduces to z squared over c squared is equal to k squared over a squared plus y squared over b squared. So if we rewrite this a little bit, moving all of our variables to one side, I would have a negative y squared over b squared plus z squared over c squared is equal to the constant value k squared over a squared. So this would give me a hyperbola. I've got different hyperbolas for different values of k. Where my z-intercepts would be at positive or negative c. Let's see, not quite here because my constant isn't 1 on that right-hand side. But nonetheless, I would have a hyperbola. So let's see if we could sketch a representative one. So if I'm taking intersections that are parallel to the YZ plane, I get these hyperbola shapes, something that looks like this. And if we consider our traces in planes that are parallel to the XZ plane, say by taking a fixed value of y, so let's say, for instance, if y is equal to k, then our equation is of the form z squared over c squared is equal to x squared over a squared plus k squared over b squared. Or again, moving everything involving a variable to one side of the equation, we would have negative x squared over a squared plus z squared over c squared is equal to k squared over b squared. So again, this would define a hyperbola. So for different values of k, I would have different hyperbolas. So if we're considering traces that are parallel to the YZ plane, the XZ plane, we would have hyperbolas that would look something like this. Now, I also mentioned that for certain traces in planes of the form x equal k or y equal k, we would have lines for our traces, in particular if k was equal to 0. So let's take a look at that. In this particular case, let's say if we were to take x equal to 0, if we're looking at the yz plane, then our equation would be of the form z squared over c squared is equal to y squared over b squared. So I claim that these represent lines. Let's see why. So if I were to simplify this a little bit, I could write this equation in the form z squared is equal to c squared over b squared times y squared, or taking the square root of both sides, I would have the absolute value of z is equal to c over b times the absolute value of y. Or maybe a simpler way to write this, z is equal to positive or negative c over b times y. So these would represent linear equations. Z is equal to some constant multiple of y, which would be defining different lines depending on what the values of c and b are. I would have a line with some positive or some negative slope in that yz plane. And similarly, if I were to take y equal to 0, if I look in the xy plane, I would get 2 lines as my traces in those particular planes. So by visualizing these traces, we can see that we would be defining a cone. Now, typically when we visualize a cone, we might think of just the upper or lower half of the figure shown here. So the way it's defined is in terms of these quadratics. If we wanted to specify, say, the upper half cone or the lower half cone from our equation, if we were to solve for z, let's say we wanted the upper half cone, I would take z as the positive square root of this term on the right-hand side. Or if I wanted the lower half cone, that is the part that lies below the xy plane where z is 0, I would take the negative square root of that expression on the right-hand side of my equation. So here, the way that it's been described as, in terms of just z squared, we're defining both the upper and lower half cones here. So when we're referring to a cone, we really mean both the upper and lower half cone. So let's look at some other ones. The next type of quadric surface that we'll discuss would be one defined by an equation of the form z over c is the sum of x squared over a squared plus y squared over b squared. So here, if we have, say, one variable, only involving the first power, is equal to a sum of squares of our other 2 variables, then we get something called an elliptic paraboloid. So if we consider the traces of this surface in horizontal planes, we get ellipses, and its traces in vertical planes, say x or y equals to k, would give us parabolas. And in this case, we would say that the axis of our paraboloid would be the z-axis. So I've given an illustration of this paraboloid below. Let's sort of justify why our surface looks like this by considering those traces. So starting with our traces in horizontal planes, if z is equal to k, then our equation is of the form k over c is equal to x squared over a squared plus y squared over b squared. So here, this would represent an ellipse. So for different values of k, we would have ellipses. Now, in this particular form of the equation, if we're assuming that c is positive, then the only way that we get an ellipse would be if or well, let me say this. In general, we would have ellipses if this constant on the left-hand side of my equation is non-negative. So here on my right-hand side, if I'm summing x squared over a squared plus y squared over b squared, well, in order to have a real valued solution for xy, that sum is non-negative, so I will only have an ellipse if this constant on the left-hand side, k over c, is positive. So if we're assuming that c is a positive constant, k would have to be greater than 0. So in the figure that I'm sketching here, I will only have ellipses if k, which is a plane parallel to the xy plane and k units above the xy plane, is positive. So we only have ellipses here in planes that lie above the xy plane, for which z is positive. And we can see that the larger that we make the value of k, the larger the area of our ellipse. So let's consider some other traces. Let's say, for instance, if we have a fixed value of x, so if we're looking at the yz plane or planes parallel to it, then the equation is given by z over c is equal to k squared over a squared plus y squared over b squared. Or rewriting this maybe just a bit, we would have z is equal to, let me rewrite it like this. I would have c over b squared, all times y squared, plus c times k squared over b squared, a squared here. So I would have z is some quadratic function of y with some constant added to it. So in a plane, these would define parabolas. For different values of k, I would just have a different intercept or a different a vertex for my parabola. So let's see if we can sketch one. So in particular, if I took k as being equal to 0, I would have z is c squared over b squared y squared. So I would have a parabola whose vertex would be at the origin, opening up in that yz plane. And if I take different values of k, so if I move forward or backward from that yz plane, well, I still get parabolas, but the vertex of my parabola might shift upward. So we would have these different sort of parabolas depending on what we choose for k. And then in my last sort of plane, if I choose a fixed value for y, then my equation is of the form z over c is equal to x squared over a squared plus k squared over b squared. Or again, solving for z, I would have c over a squared, x squared, plus c k squared over b squared. So we would have here in the xz plane or planes parallel to that, we would have an equation where z is a quadratic function of x, which would represent a parabola in that plane. So depending on what our value of k is, we would have different shape parabolas. So starting with the value k equals 0, if we're looking in the xz plane, we would have a quadratic whose vertex is at the origin. So we would have a parabola shaped something like this. And if I move outward from that xz plane, I would get parabolas whose vertex would just be a little bit larger. So we would be getting parabolas, but where our vertex lies above the origin. So looking at those traces, we see that we get a surface that looks like this. Now, one other thing I want to stress here was about the axis. So in this example, we would say the axis of this paraboloid is the z-axis. We can see here that our surface is sort of, it looks like a parabola, but in 3 dimensions, and it's opening upward along the positive z-axis. It's sort of centered about the z-axis. Now, how can we determine which axis we're centered about? Well, it would be whichever, the axis corresponding to whichever variable is not a quadratic. So if we had something similar, let's say we had x over a was equal to y squared over b squared plus z squared over c squared, we would have an elliptic paraboloid, but opening along the x-axis instead of the z-axis. So that axis where it's centered about is known as the axis of that paraboloid. Now the next type of quadric surface that we'll look at is something of the following form. So the quadric surface given by the equation z over c is equal to x squared over a squared minus y squared over b squared. So it looks similar to the equation for an elliptic paraboloid, but where we have a difference in those quadratic terms, is called a hyperbolic paraboloid. Now the traces of such a surface in horizontal planes, something of the form z equals k, would be hyperbolas, and its traces in vertical planes, x equals k or y equals k, are parabolas. So we have the surface shown here below. This type of surface is also sometimes referred to as a saddle surface. We'll see a little bit more about different types of saddle surfaces or why this would be called a saddle surface a little bit later in this course. So let's consider justifying why our surface would look something like what I've shown here. So in horizontal planes, if we have a fixed value for z, say z equals to k, then the equation for our surface becomes k over c is equal to x squared over a squared minus y squared over b squared. So we would recognize this as generally being the equation of a hyperbola, where we've got a difference of 2 quadratics is equal to some fixed constant. So let's look at these traces here. So if we're assuming that c is positive, if we have a positive value for k, then the left-hand side of our equation would be positive. So we would have a hyperbola that would look something like the following. Whereas if k becomes negative, so if we cross below the xy plane, then the direction of our hyperbola would change. So it would be opening along a different axis as opposed to the hyperbolas above that xy plane. Now let's think about our other traces. So if we were to consider a fixed value of x, say x equals to k, then our equation is of the form z over c is equal to k squared over a squared minus y squared over b squared. Or simplifying this just a little bit, z would be equal to c k squared over a squared, so some constant, minus c over b squared times y squared. So z would be a quadratic function of y, so we would have a parabola in that plane. Depending on what I choose for k, I would have different shaped parabolas. So let's consider the one in the yz plane itself. That is, if x is equal to 0, then z would just be equal to negative c over b squared y squared. So I would have a downward opening parabola in that yz plane. Or here, I guess I've switched some of my constants. Maybe c would be negative in the example that I'm illustrating here, so that this term c, negative c over b squared y squared would be positive, so I would have an upward opening parabola in that plane. So in this particular surface that we're illustrating here, this would be an example where the constant c is negative. So let's consider traces in other planes. And we can see here, of course, depending on what we choose for k, we might have a parabola with a different vertex, maybe opening a little wider if we move forward or backward from that yz plane. Now looking at other planes, let's say y equals k, we would have something of the form z over c is equal to x squared over a squared minus k squared over b squared, or rewriting this as z equals c over a squared x squared minus c k squared over b squared. Again, we would have a parabola since z would be a quadratic function of x. Now in the figure that I'm showing here, I've specified that c is negative, so z would have a negative x squared coefficient, so I would have a downward opening parabola in the case that k is 0. So in the xz plane, I get a parabola whose vertex is at the origin, opening downward. And of course, if I were to move outward from that plane, well, I would have parabolas of different vertices, but I get something that looks like this. So this is called a hyperbolic paraboloid. Now, the last general type of quadric surfaces which we might discuss are cylinders. Now when we say a cylinder, typically we would visualize a circular cylinder. However, a cylinder does not always have to have a circular cross-section. So let's consider defining cylinders more generally. So if we have a equation where one of the variables, let's say x, y, or z, is missing from the equation for a surface, then that surface is defined as a cylinder. So as an example, let's consider the following equation. Let's say x squared over a squared plus y squared over b squared is equal to 1. So if we think about that equation in space, it would define a surface. And notice that the variable z is missing. So this surface represents an elliptic cylinder. So if I think about the equation defined here in terms of x and y, well, I see that it represents an ellipse whose x-intercepts would be at positive or negative a, and where my y-intercepts would be at positive or negative b. So I would have an ellipse, let's say in that xy plane that looks something like this. But now since z is missing from this equation, regardless of the value I choose for z, that is for any plane of the form z equals k, I would have that exact same ellipse. So no matter how far I move upward from the xy plane or downward from the xy plane, I'm going to get the exact same ellipse as my trace. So here we would have a cylinder where our cross sections are ellipses, so we would refer to that as an elliptic cylinder. Now, as another example, let's suppose that we were looking at the equation y is equal to a times x squared, which we would know represents a parabola in the xy plane whose vertex is at the origin, opening upward along the y-axis. So we would here have in the xy plane something that looks like this. And since the variable z is missing from that equation, well, for any trace of this surface in a horizontal plane of the form z equals k, I would get the exact same trace. So no matter how far I move upward or downward from the xy plane, I get the exact same parabola. So here I end up with something called a parabolic cylinder. So it's a cylinder extending along this z-axis where all of my cross-sections are parabolas, so we would call this a parabolic cylinder. Now, one other thing that we can mention here is that the axis for our cylinder would run along the axis corresponding to the missing variable. So in these two examples, we were omitting the variable z, so our cylinder is running along the z-axis. But in general, if we had a different variable missing, we would have a cylinder running along maybe one of my other coordinate axes. So finally, now that we have identified the different types of quadric surfaces and discussed cylinders, let's look at some examples where we're given a quadratic equation in terms of three variables, and we have to identify the type of quadric surface that it is describing, and perhaps sketch it, so get a rough sketch. So in our first example here, we are asked to identify and sketch the surface defined by 9x squared minus y squared minus z squared is equal to 9. So if I perhaps rewrite this slightly, I could divide through this equation by 9 to put it in what we would consider maybe a little closer to the standard form for quadric surfaces that we had considered. So dividing my equation through by 9, I would have an x squared minus y squared over 9 minus z squared over 9 is equal to 1. So here I have a quadratic in terms of x, y, and z, where all of my terms are squared, and then two of these terms have negative coefficients. So reviewing the different types of surfaces that we had discussed, this is a hyperboloid of two sheets. Now here we're also told to try to sketch this surface. So when we're trying to sketch a quadric surface, sort of like we were doing in our general discussion, we might consider traces of our surface in different planes, different coordinate planes, or planes parallel to the coordinate planes. So let's consider our traces here in horizontal planes. So maybe something of the form z equals k. So if z is equal to k, then our equation becomes 9x squared, well, let me use the standard form that I had rewritten it in. So we would have, let's see, x squared minus y squared over 9 minus k squared over 9 is equal to 1. So rewriting this, we would have x squared minus y squared over 9 is equal to 1 plus k squared over 9. So this would represent a hyperbola in these planes parallel to the xy plane. So let's look at our traces in other planes. If we're considering something of the form, let's say x equals k, then our equation would be of the form k squared minus y squared over 9 minus z squared over 9 is equal to 1. Or rewriting this, we would have k squared minus 1 is equal to y squared over 9 plus z squared over 9. So this equation would represent an ellipse as long as this sum of squares on the right-hand side is equal to some positive number. So we would have an ellipse if this k squared minus 1 is non-negative, or equivalently if the absolute value of k is greater than 1. So this is why it will be a hyperboloid of two sheets. There are certain values of k such that my surface will not intersect a plane of the form x equals to k. Now in our last type of plane, if we consider a plane parallel to the xz plane, then our equation would be something of the form x squared minus k squared over 9 minus z squared over 9 is equal to 1. Or rewriting this slightly, we have x squared minus z squared over 9 is equal to 1 plus k squared over 9. So again, this would be a hyperbola. So let's see if we can use this information to try to sketch our surface. So this is going to be a hyperboloid of two sheets. So let's sketch this. We have our x-axis, y-axis, and z-axis. And we had seen that in planes that are horizontal, we would have hyperbolas. So let's consider what this would look like in the xy plane in particular. So if we take z equals to 0, we would have the following equation where k is equal to 0. So we would have an x-intercept of positive or negative 1 for our hyperbola. And it would be opening along our x-axis here. It would not have y-intercepts. Now, if we consider our trace in another plane, let's say maybe the xz plane where k is taken to be 0 for y, then we would have a hyperbola where again our x-intercepts would be positive or negative 1, and we would not have z-intercepts. So I would have, let me maybe use, well, it's fine. So I would have a hyperbola that would look something like this. And then if I consider my traces in planes parallel to the YZ plane, so looking at fixed values of x, well, I have an ellipse as long as the magnitude of k is greater than 1. So as long as I've moved outward from the YZ plane 1 unit, I would have an elliptical cross-section. So I'm going to get something that looks like the following. I'll have these little elliptical cross sections. So here a rough sketch, but I see that my surface is a hyperboloid of 2 sheets, which is sort of expanding along that x-axis. So let's look at another one. In this next example, we are asked to identify and sketch the surface defined by this equation. And what's a little bit tricky here is the fact that 2 of our variables, namely x and y, involve expressions to the first power. When we were considering the general forms or the standard forms for the equations of quadric surfaces, only one of our variables ever involved something to the first power. So what can we do in this case? Well, what I can try to do is group the terms involving x. I know, or I see in this example that even though I have something with x to the first power, there's also a quadratic term involving x. So let me try to maybe group those terms together and write it as a perfect square. So rewriting our equation, if I group the x variables, I would have x squared minus 6x, and then with my minus y plus 2z squared plus 10 equals 0. Well, I can take this quadratic involving x and complete the square. So if I complete the square in this quadratic, I would have x squared minus 6x, and I would have to add 9 here to complete the square. Then I would have my minus y plus 2z squared plus 10 is equal to. Now, if I added 9 on the left-hand side of this equation, I must also add 9 on the right-hand side to keep these expressions equal to one another. And this allows me to then factor this as x minus 3 quantity squared minus y plus 2z squared. And then if I group all my constants on the right-hand side, subtracting 10 from both sides, I would have a negative 1. Or if I solve this for y, I would have x minus 3 quantity squared plus 2z squared plus 1 is equal to y. So here I would have an equation where one of my variables involves only this first power, and it's equal to a sum of squares of the other variables. So this represents an elliptic paraboloid. So if we compare this form of our equation to the standard forms that we have discussed, we would see that we have an elliptic paraboloid, and maybe a little more information, whose axis is the y-axis here. Why the y-axis? Well, the only variable involving that first power was our variable y. So we had mentioned there that our axis for that paraboloid would be the y-axis. So in order to sketch this thing, well, let's think about traces in different planes. So if we consider let's let's say a fixed value of x, then our equation would be of the form y is equal to k minus 3 squared plus 2z squared plus 1. Or rewriting this just slightly, we would have 2z squared plus whatever k minus 3 squared plus 1 works out to. So this would be a parabola. A parabola opening along the y-axis in the yz plane, whose vertex is determined by this constant. Now, if we consider a fixed value of y, then we would have something of the form x minus 3 squared plus 2z squared plus 1 is equal to k, or rewriting this slightly, x minus 3 squared plus 2z squared is k minus 1. So this would give us a ellipse if the value of k here is greater than 1. So in order to get an ellipse, the sum of the squares on the left-hand side would have to be some positive number, which only happens if k is greater than 1. And then in our last case, if z is equal to some fixed constant k, then our equation would be of the form y is equal to x minus 3 squared plus 2k squared plus 1, which again would give us a parabola, where the vertex of the parabola is determined by whatever this constant is. So let's see if we can sketch this thing. So we have in our x, y, z space these different traces. So first off, in the YZ plane, let's think about what we might have, or planes that are parallel to the YZ plane. So here we would have, if x is equal to a fixed value of k, something of the following form, which would be a parabola. So if we look at specifically the YZ plane, that is if k is 0, we would have the equation y equals 2z squared plus 10. So that would be a parabola whose vertex would be at 10 and would be opening in this along this y-axis. Now, if we are looking at a trace in planes of the form y equals k, so parallel to the xz plane, we only get an ellipse as long as k is at least 1. So as long as we're moving at least 1 unit outward from the xz plane, we're going to get an ellipse. And the larger that I take the value of k, I'm going to get ellipses of a larger area. So let me maybe sketch these in at the end to make my figure a little easier to follow. Now, if I look at a plane of the form z equals k, so something parallel to the xy plane, then I would have a parabola opening along the xy plane, and if k happens to be 0, I would have the parabola whose vertex would be at x equals 3, and y would be 1, and this parabola would be opening in the xy plane. So let's sketch in our ellipses here. So as I'm moving outward from the xz plane, as I was increasing my constant value for y, I saw that I was getting ellipses of larger and larger area. So here's where maybe didn't give myself enough room here. But I start getting these ellipses of larger and larger area. So let me, for simplicity of visualizing this figure, maybe omit this parabola that I had drawn in the YZ plane. So here, to better visualize this, as this parabola keeps increasing, so is the area of my ellipse. And if I'm looking at my cross sections parallel to that YZ plane, well, we have these parabolas opening in the YZ plane. So we see something that looks like this, a very crude sketch here, but we see an elliptic paraboloid whose axis is along this y-axis. Okay. Now in our last example here, we are asked to identify and sketch the surface defined by y squared plus 9z squared is equal to 9. In order to rewrite this in maybe a little bit friendlier form, I could divide both sides through by 9. So I would have y squared over 9 plus z squared is equal to 1. So I have an equation that only involves the two variables y and z. It does not involve x. So recall from our discussion, we said if we're looking at a surface in space where one of our variables is missing, we have a cylinder. Now to consider what type of cylinder, we would need to examine our cross sections. And when we look at this equation, y squared over 9 plus z squared equals 1 in the yz plane, we would have an ellipse whose y-intercepts would be plus minus 3 and 0. And our z-intercepts would be 0 plus minus 1 in that yz plane. So we're centered along the x-axis here. So we have an elliptic cylinder. We would say an elliptic cylinder since our cross sections parallel to the x-axis are parallel to the yz plane would be ellipses. So an elliptic cylinder along the x-axis, since that is the missing variable. So this would be a description of our surface. And to sketch it, well, we have our x-axis, y-axis, and z-axis. And we said that we're looking at an ellipse whose y-intercepts would be at positive or negative 3. And whose z-intercepts would be at positive or negative 1. So we would have the ellipse in the xy plane, shown here. And no matter what, or in the yz plane shown here, and regardless of the value that we choose for x, we're going to get that exact same cylinder, or that exact same trace of an ellipse in any plane which is parallel to that yz plane. So we have an elliptic cylinder extending along that x-axis.